Welcome to track 4. My name is Klaus. I'm the co-founder of Rockstar Recruiting, a matchmaker of tech jobs and tech talents, and I'm your moderator today in this very track 4. It's my pleasure to welcome you in Congress House today, 10th anniversary of this amazing conference, and a plethora of great talks in this track today. And one of the highlights of mine is starting now with Valentin from Oracle. Valentin is explaining kiss fraud. Kiss fraud to me sounds like Tinder swindler, but Valentin told me it's something very different. It also involves kisses, it also involves money and scams, but it's more technical. So Oracle is using unsupervised graph data and training to identify fraudsters on the web, and those fraudsters, they want your ad revenue. And if you're in e-commerce or planning to do ads online, this topic is for you. So without further ado, Valentin, come on up on stage. And warm welcome for Valentin.
Thank you, Klaus. Hello, everyone. My name is Valentin, and I will be talking about fake ads, real money, and how we use graph machine learning to detect ad fraud. So first, I will give a small overview over ad technology in general, and then talk a bit about graph and graph machine learning at Oracle. And then the main part will be how to use these technologies to detect ad fraud. And then finally, I will talk a bit about kiss fraud, which is one of the fraud schemes that we uncovered using these technologies. So what is ad fraud? You pay me to show your ad to people, and I just show it to a computer and keep the money anyway. So this sounds straightforward, but actually it's a quite big problem. There's some estimates that around $68 billion have been lost in the year 2022 due to ad frauds. There's different types of ad frauds. So for example, botnets, where you have bots going to click on ads, click farms, humans kind of doing the same thing, but making it look a bit more organic. There can be ad injections, domain spoofing attacks, and so on. Why is this even a thing? So why is there ad fraud? One of the reasons is that the digital ad ecosystem is quite complex, as you can see here. There's many parties involved. You as an advertiser, you wouldn't directly interact with the website where you want to show your ads, but rather you might be in contact with an agency, and the agency might be working with a trading desk who is managed by a demand-side platform or DSP. And then that DSP is connected to ad exchanges and ad networks, and they do real-time bidding with the sell-side platform to figure out which is the best ad to show up on the final website. So all of this is rather complex and is automated and also really quick, or most of this is really quick. So when you open a website as a user, this real-time bidding actually happens in real time. This is, as I mentioned, a bit convoluted, and because of this, it can be a bit hard to track down fraudsters who might insert themselves into this ecosystem. And here is where we think that graph and graph machine learning fits well to solve this use case. Graph itself is a powerful tool, a powerful way to model your data, because it also lets you look at connections between elements of your data which might not be obvious from just looking at the data or just looking at your database tables and the features in there. So there's many use cases that you can solve with graph. There are the ones around cybersecurity, there are healthcare use cases, retail, financial services, and many more. And we at Oracle, we built some graph technology. So we have classical graph algorithms like PageRank, community detection, and many more, but also PGQL, which stands for Property Graph Query Language, is very similar to SQL, and you can use it to query your graphs. And then more recently, and also relevant to this talk, we are working on graph machine learning as well, and adding that as well to our tech stack on the graph part. So a bit more on graph machine learning. We have two classes of models, so to say. The first one is focused on entities in the graph, so that might be vertices. Your entities in the graph are vertices usually, and they are connected using edges. And these models, they might do classification on these elements or on these entities or compute representations on them. And for those of you who might be familiar, we have debug implementations and graph sage implementations and more. Then the second class is about graph representation learning, and there the idea is that you compute representations for entire graphs. So if you have a bunch of smaller graphs and you want to have a representation for them, then this could be one option to go about this. And this is included in some of our products. For example, you could go on OCI Data Science, so on Oracle Cloud, and try it out for free. We have this PyPGX, which is in a Conda package, and you can use it in a notebook platform and do some of this graph analysis yourself. And we also have Graph Studio, which comes with autonomous database, and so on. Right, so now back to ad fraud. How can we use these types of technologies to detect ad fraud? So the objective here is to detect invalid traffic in web impression data. And to do this, we want to use an unsupervised graph machine learning approach and to detect the actors that could be doing this IVT. And the actors in this case are IPs, so IP addresses or users surfing the web. And we are interested in finding clusters of them who might be similar, and then checking if they are involved in IVT. So I have 4 phases to go over. The first one is graph creation, or how do we put our data into a graph. The second one will be representation learning, computing embeddings or vector representation for these IPs. Then explainability, to better understand these embeddings. And then finally, actually looking at the results and trying to figure out if this is IVT, invalid traffic, or not. Okay, the first phase, graph creation. What is the data that we are working with? We get a bunch of sessionized impressions, and you can imagine this as being triples of IP, timestamp, and domain. So you know at this point in time, that IP was interacting with that website and interacting with the ads on that website. And then having this data, we can extract a unique set of IPs out of it and have them be one side of the graph. So we create a bipartite graph, and then the unique set of domains would be on the other side, and then we connect them using these edges in between. So graph is a good idea here in our opinion because it lets us also look at the co-visitation patterns, so which IPs are actually visiting similar domains than other IPs, and what are the features on there. So this graph structure is also augmented with additional features that we can add to the graph, and this will help later on the model to learn useful representations. Okay, now the second phase, it's about this representation learning that I mentioned, and what this does is using the graph structure and the features to compute embeddings or vector of numbers for these IPs. And to do this, we want to use an unsupervised approach. And I want to comment a little bit on this because actually we would have some labels here. So we could, in theory, also train a supervised model. But the labels, they come from other pipelines that also try to figure out, is this fraud or not? And then if we were to use these labels to also train this graph machine learning model, then the resulting model might only be as clever as these labels. So here, instead, we want to use an unsupervised approach to also kind of cover a bit other types of fraud. Because as you can imagine, fraudsters will also dynamically come up with new things to conduct this fraud. So how does it work? On a high level, you can see on the diagram on the bottom, we have an IP vertex in the middle. Then the first thing we do is we sample around this IP a neighborhood. And in our case, the neighborhood is, of course, the domain vertices that are connected to this IP. Then in the middle, you can see the architecture of the model. So we feed these domain features through this aggregation layer. It gets you out an intermediate representation from this neighborhood. Then this neighborhood will be concatenated with the IP features itself and then fed through some embedding layer to get out the final IP embedding. Now, having this embedding, like this is the forward pass of the model. We can do this after having trained it for all the IPs. We get all the embeddings for all the IPs. Then we can use a simple clustering algorithm to cluster together IPs that are behaving in a similar way. So similar, what does it mean? It could mean they have similar IP features. It could mean they have similar connectivity to domains, like doing similar access patterns. Or it could mean that just the domains that get accessed are also similar, because we feed in the domain features as well. So the assumption really is that the cluster here contains similar IPs, and we want to look at clusters to figure out if they're IVT or not. Okay, so we have now these clusters, but we don't really know what are these clusters about. So why why was an embedding created as it was? It's not really that clear. So this is why we have this GNN explainer module that we can add on top of this unsupervised graph machine learning model that I mentioned before. And what this one does, it creates you importance scores of the most influential neighbors and the most influential features that were involved in the computation of this IP embedding. And as you can see on the side there, the model or the architecture looks the same, but just as an add-on, we have now these red bars, which signify these importance scores. And how it works is that just instead of passing in the features as is into the model, we first multiply it with this learnable importance score weights, and then only pass it through the rest of the model. So you can imagine that if something is not important, this score will actually go down to 0, and the feature will not actually contribute to the embedding. And this is actually trained using this contrastive loss. So if you look at the clustering, we want to find these importance scores such that the embedding is actually closer to its cluster centroid. So it means that it is a kind of amplifying the semantics of it, or of what this cluster means. Okay, so the important thing here is that we know which are the most important neighbors of this IP and which are the most important features of this IP. And this will help us later on in the investigation. So now, investigation. What do we do? So this phase 2 and phase 3, we do it on a weekly basis. So we have this trained model, and then every day we will create a new daily graph, and we will do the inference using this trained model. Then we do this clustering, as you see on the side there. We have all these clusters, and now, the problem is there's too many clusters. We cannot really look at all of them. So which cluster should we actually look at? And here, what we came up with is a simple heuristic that we just look at which of the clusters have already been tagged with IVT using other techniques. And then we look at which cluster is actually similar to that cluster, but it hasn't already been tagged. So that might be an interesting cluster to look at, because clearly it is doing something, or maybe not clearly, but it looks like it is doing something suspicious because of the similarity, but it hasn't already been detected before. So this is something we could look at. And then what does it mean to look at the cluster? It means we look at the explainer output, so which were the most influential domains. We can go to these domains, look at them, what is there. Sometimes it looks quite suspicious because there is full of ads and clearly not intended for people to actually use this page. We can also look at the graph itself. So for example, IP patterns or IP access patterns. If it's very regular, it could mean maybe it's a bot. So all of these factors can play into here. But this last step, it is still something that an investigator needs to look at. Okay, so what did we find using this? We call this fraud scheme KISS fraud. And why the name? Because the domains that are involved in here are like have something with KISS in the name. So that's where the name comes from. And what is the fraud about? So imagine a person wanting to look or wanting to watch movies for free. They might end up on this page kimcartoon.li, and then they scroll around until they find their movie. Then they click on their movie, and then what happens is that they get redirected to another page called kisscenter.net in this case, but the page still looks the same as before. So for that user, actually, it doesn't really matter too much. But for advertisers, this matters because kisscenter.net, if you go there directly and not via this movie page, then you will see that it looks like a news page. So they're kind of selling the ads on a news website. And then if like some automated tools might even check the context on there, you would see a news website. So it looks fine for advertisers to put their ads on there, but actually the ads are shown next to illegal content, which advertisers usually don't want to do because it's not brand safe. So yes, this is kind of the fraud here. And yes, we uncovered this last year, and we identified some of the domains that were involved in here, and some of the customers, so supply or sell-side platforms, actually a sizable amount of their traffic was impacted by this fraud. So you see there 11 and 16%. So of course they got notified, and then they could take the necessary steps to mitigate there. Yes, and I also have like a small video of how this looks in action. So you can see now we go to this KISS TV show page. We scroll until we find some interesting series. Now clicking on the series, it will redirect. And I'm not sure if you can see it, but the domain changed now to KS News, and it's not a KISS TV show anymore. But still it looks the same for this user that wanted to just watch something for free. And now showing that if we take the same link and go to another window, the same link will show you some news site. I mean, it does look a bit cheap, but still it looks like a news site. Right, so this was the talk about ad fraud. So if you have any questions on this or on Graph, feel free to ask here. Or otherwise, if you would like to talk to us, please come to our booth later on, and we can also talk a bit more about different use cases there. Thank you.
Thank you, Valentin. First of all, it's a tradition in Swiss Data Science Conference that you get a gift for your talk.
Thank you very much.
And now we open the floor for questions, of which I'm sure there are many. Yes, there's a microphone coming.
What is the size of your data set? Yeah, if you can comment a bit on any limitation you might have in that regard. Yeah.
So this is actually sampled down a bit. So we look at only IPs that are like in a specific, like they do a specific amount of traffic per day, because we saw that it's like most likely that we find fraud there. But if I remember correctly, it's like in the millions of IP vertices, and domain vertices will be a bit less. And then edges are also up in the millions per day.
Hi, thanks for the presentation, first of all. Can you comment a bit more about the clustering? So how do you define number of cluster and which algorithm are you using?
Yeah, so the clustering is very simple in this case. So we just use k-means, and I think we experimented out with what number of cluster works best in practice, and we found that 50 is usually a good way to go about. So we haven't really looked into more sophisticated ways to do the clustering, but I think that could certainly be a way to improve this. Thank you.
More questions?
Thanks.
Can you maybe comment on the dynamic nature of your graph? Can you do this thing in real time when you have new IPs coming in or new domains, or do you have to do it in a batch?
So in this case, we're doing this on a daily basis. So basically, this data gets fetched, and then on a daily basis, we have like some jobs that produce this graph, and then we just do the analysis on that. But we do have some ways to like dynamically add to an existing graph, but we're not using this in this case here.
Thank you for your talk. You mentioned features of the domain nodes. What features were those?
Right. So on the features, we are not actually engineering them ourselves. So it's like another team who is doing this. So I don't know like all the details there, but it can be many different things. It could, for example, be some metrics around the density of the ads that would be on that website, or maybe something about average scroll speed that they measure on this website. Thanks.
Another question? One is over there.
Thank you for your very interesting talk. So your use case was fraudulent sort of like advertisements next to fraudulent content. But I mean, brands, it doesn't just necessarily need to be fraud. So I was wondering if you're thinking about extending this use case to other scenarios that hurt the brand reputation.
Yes, so there's another like bigger team at Oracle working on this advertisement use cases, and I think this is just a very thin slice of this. They have like many other things that they also like have ongoing there, but I don't really like know all of them that I could now list them off here.
Hello. Sort of a follow-up question to the features engineering. So you mentioned the features on the vertices or the nodes of the network, but do you also have features on the edges?
So at this point, we just have the timestamps on the edges. And like one of the reasons is because the edges are, like we have more edges than vertices. So kind of we like put more features on the vertices. Because of that reason, we can like scale a bit more. But it would definitely be an idea to also experiment a bit more with putting features on the edges. Like some features would be more natural to not aggregate them and have them be on a per session level. So I think that could be something to try here.
What's the future? Won't fraudsters imitate humans more and more, and then your graph it gets harder and harder to separate the humans? And will we have to do captures before seeing ads, or how do police and fraudsters?
Yeah, I think fraudsters like become also more sophisticated as time goes on. There's more techniques out there that they could also use to do the fraud. So I think to catch the fraudsters, we also need to like keep up to date. Maybe also innovate a bit more on the models that we are better equipped to catch these things.
Cool, thank you. Last questions, maybe? Yeah, there's one. Sorry.
What advantage does your approach have of doing representation learning and then k-means over more, say, traditional graph methods like community detection, analyzing homophily and stuff like that?
Right. Yeah, I think it can maybe catch some more like unseen things as well. But the other approaches would also be valid, I think. So probably it would be best to do something in conjunction with machine learning and also other approaches. Like maybe have some additional features using traditional approaches, then feed that into the machine learning model to get the best out of it.
Thank you very much. So now it's 10:50. You have time to switch the room, which I totally do not recommend. Or you can tell the others about track 4, and we will reconvene at 11 with the next talk. Thank you very much.